Howdy folks, Mr. Reed here, and welcome to one more question. So, what we're going to be doing right now is taking a look at an equation that is built off of some exponential expressions. We're going to be looking at giving this an exact value answer, not an estimate. And by doing that, we're going to be using logarithms to represent our answer properly. So we're going to do just a really simple expression. So this is a mild level video, and so if you're looking to do an exponential based equation, solving for the variable and using logarithms to do it, you're in the right place. So let's get to it. All right, now this one is going to be 7 to the power of x plus 3 is equal to 10. Nice, simple, small expression. Now, right from the get-go, what we should try to do, especially if we're kind of comfortable with this sort of thing, is see, can we express the base on both sides of our equation, or the exponential statement, or whatever's there, with the same base. So can I express 7 to the power of something as the same base as 10 to the power of something? Well, not nicely, not with nice whole number values. So that is kind of thrown out the window right away. So instead, what I'm going to do is try to write this. You could think about writing it in logarithmic form, actually, and that would be fine. That's one way to approach it. The other way is to apply a logarithm on both sides of my equation. That's the way that I'm going to look at it. I usually like the idea of applying an inverse. So in this case, the inverse that I'm going to apply is the log base 7. And if you're worried about applying a logarithm on both sides of the equation here, the exponential function on the left is always positive. That is it's shifted 3 units to the left. Base 7 to the x function, which is a growing function. Its range is greater than y greater than 0. So that's going to be safe all the time. And then, of course, log base 7 to 10. It's just a single constant positive value. So that one's okay too. So we're going to stuff this thing inside of the logarithm. And of course I can do this because the whole point of having an equal sign in the first place is that the two sides of that equal sign are equivalent. They are the same. So if I put one of them inside of the log base 7 and put the other one inside of a logarithm base 7, they're supposed to be equal. So there we go, still equal. Now, log base 7 of exponential 7, base 7, is, again, inverse functions. So it's going to cancel each other out, and we'll be left with the value that was inside the argument, which is an x plus 3. On the other side of my equation, that is actually, and as you get used to this, it kind of is a weird thing. That is an irrational number. At first, when you're talking about irrational numbers that are, for instance, square roots, and somebody comes along and says, oh yeah, well that's just the square root of 3. And you're like, well, what's that mean? Well, it's a really cheesy answer at first, because if you say, what is the positive value that when multiplied by itself gives you 3? So I know there's a positive and a negative answer. I'm going to just say, what's the positive value? Well, that is when x is equal to the square root of 3. So you're basically saying, what is the number when multiplied by itself gives you 3? Well, it's the number that when multiplied by itself gives you 3, which is the definition of what the square root means. So the square root of 3 is the square root of 3. I don't know. It's kind of weird to say out loud. But the idea is that the answer is the notation for the answer, which is a little bit awkward because you're not really solving anything. You're just stating notation. But we get really used to this because we recognize that square root of 3 is the way that we write that number. That is the best, tidiest, most recognizable way to write the value that is represented by that little equation. This is also an irrational number that is best represented by saying something like log base 7 of 10. You could use different logarithms to represent it if you use a change of base, for instance. But this is as a single logarithm, so it's pretty nice the way that it is. While it's pretty nice, it does take some getting used to the fact that that actually is our final answer in this particular case, or at least the final expression for the logarithm part. Of course, I kind of went off on a tangent there for a moment. I still need to solve for x, and if I do that, I'm going to get x is equal to log base 7 of 10, and then minus 3 kicking around as well outside of the logarithm because I need to subtract 3 from both sides, and that's what I would get as an expression. This might seem not so great. Don't worry about that. It's perfect. So we're going to have expressions that look like that, and that's totally okay. That is the best way, I think, to write down that answer. If what you really wanted to do was give a decimal estimate for what that value is, you would grab your calculator, and you would either be super lucky that your calculator is one of the newfangled ones that allow you to actually adjust the base on your logarithm, or you'd use a change of base. I really like the natural log, so I would say ln 10 divided by ln 7 minus 3, and that's what I would put into my calculator. I'd get an estimate of what the value of x was, put it to however many decimal places I'm either asked to do or makes me feel comfortable, if I need some particular amount of accuracy. But for me, I like the boxed answer better because I like exact values. Even though if you were doing some sort of actual application with this, nothing really can be measured exactly. So it's all relative, I suppose. All right, so that is solving an exponential based equation by using logarithms, and it's an easier thing. But hopefully you found that one to be pretty smooth. If you enjoyed this or found it useful, like, subscribe, and as always, take care, folks.